Hello friends, welcome to my lecture on Laplace equation. This is third lecture on Laplace equation. We will be considering Laplace equation in spherical coordinates in this lecture. We know that the spherical coordinates r, theta, phi are related to the Cartesian coordinates x, y, z by the equations x equal to r cos phi sin theta, y equal to r sin phi sin theta, z equal to r cos theta, where theta is the polar angle, phi is the azimuthal angle. You can see, suppose we take this point P here, whose Cartesian coordinates are x, y, z, and polar coordinates are spherical polar are r, theta, phi. Then this is your orthogonal projection P dash, B join origin to P dash, then this is r, draw lines through P dash parallel to x and y axis, then this is x, this is y. So, OA is x, OB is y, and OZ, this is C. Okay. So, this is point C, this one. Okay. So, this is your OC is Z, and this angle is theta, okay, and this angle is phi, because phi is the azimuthal angle, this angle is theta. Okay. So, then what we notice is that this is r, OP is r. Okay. So, OP is r, therefore, and this z axis makes angle theta with OP. So, z is equal to r cos theta. Now, when this is r cos theta, OC is r cos theta, this is r sin theta. So, this is also r sin theta. So, OP dash is r sin theta, and therefore, the components of OP dash along x and y axis are x r sin theta cos phi, and r sin theta sin phi. So, this is x is r sin theta cos phi, and y is r sin theta sin phi, and then z is r cos theta. And when we find the Laplacian of a function u x by z in spherical coordinates, what we notice is that del square u is u r r. U r r is partial derivative, second order partial derivative of u with respect to r, as usual. Okay. This is first derivative of u with respect to r. So, 2 over r u r 1 over r square, then this is second order partial derivative of u with respect to theta, then cot theta over r square, first derivative of u, first order derivative of u with respect to theta, then 1 over r square sin square theta, u phi phi. U phi phi is second order partial derivative of u with respect to phi. We are taking this without proof, because its proof is very lengthy. So, we may also write the Laplacian of u. Now, you can see the terms u r r plus 2 over r u r can be expressed as 1 over r square times partial derivative with respect to r of r square del u over del r, and then here the two terms 1 over r square u theta theta plus cot theta over r square u theta is nothing but 1 over r square times 1 over sin theta, partial derivative with respect to theta of sin theta, del first derivative of u with respect to theta, and the last term is 1 over r square sin square theta u phi phi. So, this equation can also be written in this form. Now, we will come across several problems where the potential will be same at similarly situated planes in all the planes passing through a particular axis. So, if you take that axis as z axis, then you will depend only on r and theta, it will not depend on phi. So, in such a case the partial derivative of u with respect to phi, second order partial derivative of u with respect to phi will be 0, and therefore, Laplace equation 1 will reduce to u r r plus 2 over r u r plus 1 over r square u theta theta plus cot theta over r square u theta equal to 0. So, we will have this equation. Now, let us study how to solve this Laplace equation by separation of variables method. So, let us assume the solution of the equation 1 to be product of r g theta h phi. We are using separation of variable methods. So, let us take r to be a function of r only, g to be a function of theta only, h to be a function of phi only, and then substitute this u r theta phi equal to r g h into the equation 1. Okay. So, let this be the solution of equation 1, then substituting it into 1 and dividing by r g h. You can easily verify that what we get is 1 over r square d square r over dr square plus 2 r dr by dr plus 1 over g d square g by d theta square plus cot theta dg by d theta plus 1 by h sin square theta d square h by d phi square. Now, this equation can be written as you can multiply it by sin square theta. So, when you multiply by sin square theta, what you get? Sin square theta into 1 by r square d square r over dr square plus 2r dr over dr plus 1 over plus sin square theta over g into d square g over d theta square plus cot theta dg by d theta equal to minus 1 over h d square h over d phi square. Now, you can see left hand side is a function of r and theta only, right hand side is a function of only phi. So, this can be possible only when both are equal to a constant. So, let us take this equal to a constant, say k, then what we will have? D square h over d phi square equal to minus k h. So, we will have d square h over d phi square equal to minus k h, or we will have d square h over d phi square plus k h equal to 0. Now, the boundary conditions that are given in so for in the case of a physical problem, we shall see that the case k equal to 0 is not possible, and the case k equal to mu square, if you take k equal to mu square, you get h to be, let us take k equal to mu square, then you will get h equal to a cos mu phi plus b sin mu phi. Okay. So, like what I have written here, 1 over h d square h over d phi square equal to minus m square. Okay. So, you take k to be mu square, then you get this solution, and for this solution what we will need, that because the potential is a single valued function. Okay. So, h phi plus 2 phi should be equal to h phi, and therefore, what we will have this mu, here I have written mu, but here it is m. So, this mu, or you can say m, must be an integer. So, let us see, we will have h equal to some constant into cos m phi plus d sin m phi, if we take this equal to minus m square. Okay. So, then what we will have, this because of h phi plus 2 phi equal to h phi, m must be taken as an integer. Now, what happens when you take this as minus m square? Okay, 1 over h d square h over d phi square as minus m square, you take 1 over r square d square r over dr square plus 2 r dr over dr equal to n into n plus 1. Why we take it as n into n plus 1? It will become clear later on. So, what we will have, you will have 1 over r square d square r over dr square 2 r dr over dr. So, as n over n plus n into n plus 1. So, we will get n into n plus 1 n into n plus 1 okay. So, n into n plus 1 plus 1 over g d square g over d theta square okay, plus cot theta dg over d theta. 1 over h d square phi over d phi square we have written minus m square. So, we will have minus m square over sin square theta equal to 0. Okay. So, this can be written as d square g over d theta square plus cot theta dg over d theta plus n into n plus 1 minus m square upon sin square theta into g equal to 0, which is a Legender's equation. So, we will discuss that later on, and so let us see when we write this equation equal to n into n plus 1, what we get. Now, here the point is why we are not taking it as plus m square. If you take it as plus m square, then what you will get, d square h over d phi square minus m square h equal to 0. If instead of minus m square, if you take plus m square here, then what we will get? So, the solution will be h phi equal to a e to the power m phi plus b e to the power minus m phi, because the auxiliary equation will have two real distinct roots plus minus m. Now, here when you, because we require that h phi plus 2 phi be equal to h phi. Okay, so, this cannot be fulfilled here, h phi plus 2 phi equal to h phi, and therefore, taking 1 over h d square h by d phi square to be positive m square is not appropriate. Now, let us look at this equation, 1 over r square r double dash plus 2 r dr over dr. So, this can be expressed as r square d square r over dr square plus 2 r dr over dr minus n into n plus 1 r equal to 0. Okay. So, let us discuss how we solve this in the next slide. So, r square d square r over dr square plus we have 2 r dr over dr Okay. So, let us put r equal to e to the power z. Let us change the independent variable from r to z. Then what we will have, r square d, because this is Cauchy-Euler equation. So, r square d square r over dr square will become d into d minus 1 r plus 2 dr minus n into n plus 1 r equal to 0. R I can write it as d square minus d plus 2d minus n into n plus 1 operating on r equal to 0, and what we get then d square minus plus d minus n into n plus 1 r equal to 0. Okay. So, in order to find the solution of this, now this is a linear differential equation with constant coefficients. So, we write the auxiliary equation m square plus m minus n into n plus 1 equal to 0, and what we can do, we can write it as m square minus n square plus m minus n minus 1 equal to 0. No, m square minus n square, and then what we will get, m minus n, only m minus n is left. Okay. So, this is m minus n into m plus n, and we have m minus n here. So, taking m minus n common, we get m plus n plus 1. Okay. So, there are two roots of the auxiliary equation, m equal to n and minus n plus 1. So, the general solution of this equation is r in z, okay, is equal to some constant, let us say a e to the power mz m1z plus b e to the power m2z. m1 is say n, so a e to the power nz plus b e to the power minus n plus 1 into z. Now, e to the power z is equal to r, Okay. So, this implies replacing z by r, we get a r to the power n plus b r to the power minus n plus 1. So, this is how we get r value of r. H we have already seen, h is equal to c cos m phi plus d sin m phi, and then the remaining the expression in theta gives us this differential equation. Now, this differential equation is a associated Legender's equation. We can arrive at this equation using the Legender's equation. Legender's equation is given by 1 minus x square by double dash minus 2x by dash plus n into n plus 1 by equal to 0. Let us differentiate this equation m times by using the Leibniz rule. So, then when you use the Leibniz rule, you get 1 minus x square by m plus 2 minus 2 times m plus 1 x by m plus 1 plus n minus m into n plus m plus 1 by m equal to 0. And here when you put dm y over dxm, that is the mth derivative of y equal to u, but you get is 1 minus x square u double dash minus 2 m plus 1 x u dash plus n minus m n plus m plus 1 u equal to 0. Next, let us put g equal to 1 minus x square to the power m by 2 u in the above equation. So, we change from u to g, okay, by making this substitution in the above equation. Then we get 1 minus x square, okay, g square, g double dash means d square g over dx square minus 2x dg over dx plus n over n into n plus 1 minus m square upon 1 minus x square into g equal to 0. Now, we put x equal to cos theta. So, we change the independent variable from x to theta here, and when you change the independent variable from x to theta, you can verify what we get is d square g over d theta square plus cot theta into dg by d theta plus n into n plus 1 minus m square over sin square theta into g equal to 0. And its solution now is, this is now associated Legender's equation. Its solution is g equal to e p n m cos theta plus f q n m sin theta. Now, let us, so we have the values of r, g and h, all of them. Let us multiply r, g and h, then we get a solution of Laplace equation, which we call as a spherical harmonic. Now, find the potential. Let us discuss a problem. Find the potential in the interior of a sphere of unit radius when the potential on the surface is cos square theta. So, if you take the surface or the center of the surface at the origin, okay, let us take the center of the sphere as the origin. Okay, we observe that here f theta is equal to cos square theta. The radius is unity. Okay, so we observe that the potential is same at any point because it is independent of phi. Okay, on the surface f theta is cos square theta. The potential is cos square theta. So, the potential u will not depend on phi. So, hence the Laplace equation reduces to u r r plus 2 over r u r plus 1 over r square u theta theta plus cot theta over r square u theta equal to 0. Now, we have to find solution of this equation. So, let us take u to be a function of r and theta. So, u equal to r r g theta. You put it in this equation, what we will get is 1 over r square d square r over dr square plus 2 r dr over dr minus 1 over g d square g over d theta square plus cot theta dg over d theta. Now, this is a this quantity on the left depends on r, the independent variable r only, the right hand side depends on theta only, both are equal. So, they must be equal to a constant. So, they are equal to a constant, let us say k. Okay, let us take k equal to n into n plus 1. By taking k equal to n into n plus 1, we know the equation this one, r square d square r over dr square plus 2 r dr over dr minus n into n plus 1 into r is a Cauchy-Euler equation whose solution we know, that is solution is a r to the power n plus b times r to the power minus n minus 1. So, that is the solution of this equation 3 we have already discussed, and d square g over d theta square plus cot theta dg over d theta plus n into n plus 1 g equal to 0, which we get the other equation that we get here, okay, that changes to this equation. If you put cos theta equal to V in this. Okay. So, taking cos theta equal to V, this equation changes to, so we are changing the independent variable from theta to V now. So, 1 minus V square d square g over dV square minus 2V dg by dV plus n into n plus 1 g, which is equal to 0, which is the Legendre equation. Okay. So, which is the Legendre equation. Its solutions are the Legendre polynomials P n cos theta where n takes value 0, 1, 2 and so on. So, we can obtain therefore the expression for u r theta. U r theta is r r into g theta. So, a r to the power n plus b upon r to the power n plus 1 P n cos theta, where n is equal to 0, 1, 2 and so on. Now, because our region includes the origin r equal to 0, r equal to 0, r is 0 at the center of the sphere. So, we want the solution to be finite, and when we want u to be finite at r equal to 0, we must take b equal to 0, otherwise if b is not 0, this u cannot be finite at r equal to 0. So, we must take b equal to 0, and therefore, we have u r theta equal to sigma n equal to 0 to infinity a n r to the power n P n cos theta. Now, on the boundary of the sphere, we are given the potential to be equal to f theta, that is cos square theta. So, taking r equal to 1 in this equation, what we get, cos square theta equal to sigma n equal to 0 to infinity a n P n cos theta, which is Fourier Legendre expansion of cos square theta. And we know that in the case of a Fourier Legendre expansion of a function f theta, okay, what we get is this formula. So, a n can be computed, a n, these constants a n can be computed by the formula n plus half minus 1 to 1 f x p n x dx, where x is cos theta. Now, we are given that on the boundary f theta is cos square theta. Okay. So, f x on f x is equal to now here f x is what, f x equal to f x becomes cos square theta when x is equal to cos theta. Okay. So, you should write f x becomes cos square theta. Let me write f x equal to x square. So, okay. So, what I mean is that on the boundary the temperature is cos square theta. So, f x becomes x square, because when your f x is x square, f cos theta becomes cos square theta. So, f x is equal to x, f x gives cos square theta when x is equal to cos. So, this is x square actually, f x is equal to x square which is cos square theta. Okay. So, f x is equal to x square gives cos square theta when x is cos theta. So, this formula actually is for here we need we have f x here, okay, and we have sigma n equal to 0 to infinity a n p n x. So, it is the formula for that. Now, here in place of x we have cos theta. So, we need to write the corresponding formula in terms of x. So, n plus half minus 1 to 1 x square p n x dx, and now what we do, we remember that in the case of Legendre polynomials p n x, p naught x is equal to 1, while p 2 x is 1 by 2 into 3 x square minus 1. So, we can express x square as 2 times p 2 x plus 1, okay, 2 times p 2 x plus 1 divided by 3, or we can write it as 2 times p 2 x plus p naught x divided by 3. So, in x square will be replaced by 2 over 3 p 2 x plus 1 over 3 p naught x into p n x. Now, let us recall the orthogonality property of the Legendre polynomials. The orthogonality property is that minus 1 to 1 p n x into p m x is dx is equal to 0 whenever m is not equal to n, okay, and this is 2 over 2 n plus 1 when m is equal to n. Okay. So, applying that what will happen, integral over minus 1 to 1 p n x into p 2 x will be 0 for all n other than 2. Okay. So, and when n is equal to 2, integral over minus 1 to 1 p 2 x into P2x, that to P2 square x, P2x square can be computed from here, it will be 2 over 5. Okay. And similarly minus 1 to 1, P naught x into P n x will be 0 for all n not equal to 0, and when n is equal to 0 we will have minus 1 to 1 P naught square x, and P naught square x will be 2 over 1, so it will be 2. Okay. So, using the orthogonality property of Legendre polynomials, we get a n equal to 0 for all n except n is equal to 0 and 2. So, let us find a naught. Okay. We can find a naught here. A naught is equal to, put n is equal to 0, so 1 by 2, we are taking n equal to 0, n equal to 0 means we will have 1 by 3 integral over minus 1 to 1 P naught square x dx. So, this will be 1 by 2 into 1 by 3 integral over minus 1 to 1 P naught square x dx is 2. Okay. So, we get 1 by 3. And A2 we can similarly find, A2 will be 2 plus half, so 5 by 2 into 2 by 3 integral over minus 1 to 1 P2 square x dx. So, this will be 5 by 2 into 2 by 3 into, and when you take n equal to 2 it is 2 by 5. So, we get 2 by 3. So, we know the values of A naught and A2. And so, we can write the expression for u or theta. So, what will happen? We have A naught equal to 1 by 3, A2 equal to 2 by 3, u or theta will then be A naught into r to the power 0. Okay. We will have u or theta equal to a n is 0 for all n except n equal to 0 and 2. So, we have A naught r to the power naught P naught cos theta plus A2 r to the power is 2 P2 cos theta. We have found A naught equal to 1 by 3, A2 equal to 2 by 3. So, this will be 1 by 3 P naught cos theta plus 2 by 3 r square P2 cos theta. Okay. So, let us go there. We have 1 by 3 P naught cos theta plus 2 by 3 r square P2 cos theta. Okay. Now, we know P naught x is equal to 1. Okay. So, P naught cos theta is also 1. P naught cos theta is 1, and then we know P2 cos theta, P2 x is equal to 1 by 2 3x square minus 1. So, P2 cos theta will be equal to 1 by 2 3 cos square theta minus 1. So, let us put these values. So, u r theta will be equal to 1 by 3 B naught cos theta is 1 plus 2 by 3 r square, and P2 cos theta is 3 by 2 cos square theta minus half. So, what do we get? 1 by 3, 2 by 3 r square we multiply, 2 by 3 will cancel with 3 by 2, we get r square cos square theta, and then 2 by 3 into r square we multiply to minus half. So, what do we get? 2 will cancel, we get minus 1 by 3 r square. So, we get 1 by 3 r square times cos square theta minus 1 by 3. Okay. In view of P naught x equal to 1, P2 x equal to 1 by 2 3x square minus 1. So, this is the solution to the given problem. Now, let us find the gravitational potential of a uniform disk of mass m and radius a at any external point. So, let us take the center of the disk as the origin and the normal there as the z axis. Let us look at, this is the figure. Okay. So, this is the disk and this is the center of the disk, and this axis normal line at this point is the z axis. by symmetry the potential u at any point p r theta phi will depend on r and theta only because of the symmetry of the disk. So, hence we have to solve the equation u r r plus 2 over r u r plus 1 over r square u theta theta cot theta over r square e theta equal to 0. Again let us put u r theta equal to r r into g theta, then the solution of the Laplace equation appropriate to the problem is given by u r theta sigma n equal to 0 to infinity a n r to the power n b n upon r to the power n plus 1 p n cos theta. Now, in order to obtain the values of a n and b n, let us obtain the potential of the disk at a point n on the z axis. So, for this what we do is we take a small element here at a distance rho from the center and making this angle is, let us say this element rho d rho d phi, okay, rho d rho d phi we take, and then for this element what we will have the potential of an element rho d rho d phi of the disk at n, at the point n, okay, will be equal to gm over pi a square rho d rho d phi into 1 by root z square plus rho square. Root z square plus rho square is the distance of the point, okay, this distance, okay, this distance is root z square plus rho square. So, we have 1 over root z square because we know that it is the potential is gmm over r, okay. So, this is actually r is under root z square plus rho square, and this gives you gmm over r. So, hence the potential of the whole disk is gm over pi a square integral over 0 to 2 pi integral over 0 to a rho d phi over under root z square plus rho square. Now, this we can easily integrate, and when you integrate what we get is 2 gm over a square under root z square plus a square minus z. Okay, now what we have when z is greater than a, we have 2 gm over a square z into 1 plus a square by z square to the power half minus z. Okay. Here we are integrating with respect to rho. Okay, yeah. So, what we have, let us look at this. This expression under root z square plus a square, if z is greater than a, can be written as a times under root 1 plus a square by z square, and 1 plus a square by z square to the power half, then we can write its binomial expansion and we get 2 jm by a square 1 by 2 a square by z minus 1 by 2 into 4 a 4 by z cube 1 into 3 2 4 6 a to the power 6 upon z to the power 5 and so on the z axis at the point n. Okay. Let us look at the figure. At the point n, theta is equal to 0 and z equal to r. So, r is equal to z, okay. This distance, this is r, okay, which is z. So, what we will have, so this reduces to this solution reduces to a n z to the power n, because r becomes z, a n z to the power n, b n z to the power n plus 1, and theta is 0. So, p n 0 is always 1, and so u r theta becomes this. Now, comparing 5th and 6th, let us compare 5th and 6th. When you compare, you see that b n is equal to 0 when n is odd, okay, because we have only odd powers of 1 over z here in this expression, okay. In this infinite series only odd powers of z are present. So, when n is odd, okay, then n plus 1 will be even. So, b n is equal to 0 when n is odd, okay, b n is equal to 0 when n is odd, a n is 0 for all n, because there is no term in positive integral powers of z. So, a n is equal to 0 for all n, and b n is equal to 0 when n is odd, okay, and we can write the values of b naught, b 2, b 4 from here by comparison, okay. So, we have b naught this, b 2 this, b 4 this, and therefore, for r greater than a, okay, r greater than a, u r theta is equal to this one. U r theta gm by r 1 minus 1 by 4 a square by r square p P2 cos theta, we can put the values of B0, B2, B4 in this expression. Okay. Now, when we have z less than a, okay, when we have z less than a, that is n is at a distance less than a from the center of the sphere, then we will have 2 gm by a square. Again look at this expression, 2 gm by a square under root z square plus a square minus z. So, this time z is less than a. So, we shall write a we will take outside the square roots. So, a under root 1 plus z square by a square we shall consider. So, a times under root 1 plus z square by a square, z square by z by a is less than 1. So, we can again expand it by binomial expansion, arrive here, again compare this with the equation 5, this equation, okay, because we are getting this expression for at the point n. Now, here what is happening is you can see we have a naught equal to, a naught is the coefficient of z to the power 0, a naught is the coefficient of z to the power 0. So, a naught is present there, but a1, a2, a3 they are all zeros, because the powers of z in positive integral powers of z are absent in that expression. Okay. So, we have this one, we have positive integral powers are there, negative integral powers are not there. So, Bn is equal to 0 for all n, a naught is 2 gm by a, a1 is minus 2 gm by a square, a2 is gm by a cube and so on. So, the solution for r less than a is u r theta equal to this. So, with this I would like to end my lecture. Thank you very much for your attention.